Um, Hi, I'm just going to wait for a few more minutes to see if a few more people are going to join. So just give it maybe a minute or just 2 minutes and see if more people join. But yes, welcome to the GCSE Physics Magnets and Electromagnetism class. Can you hear me okay? If you can hear me, if you could just write something in the chat, that'd be great. Oops. You can hear me? Are you able to hear me okay? Yes, okay, good. Thank you. Okay. Let's give it one more minute, see if anyone else is joining. So we're just redoing this session because I was having internet issues last week. So we weren't able to complete the lesson. But I'm hoping the internet works fine today. Okay, I'm gonna make a start, and if anyone else wants to join, then they can. Okay, so today we're going to be looking at magnets and electromagnetism. So so the points today we're going to be looking at are looking at permanent magnets and induced magnets. We're going to be looking at motor effect. And then we're going to have a look at electromagnets. And then the last thing will be transformers. We will be doing a Kahoot at the end as well. So yes, let's move on. So if you have any questions, just put them into the chat. And like I said, we will be doing a Kahoot, and there'll be top tips dotted around the session as well. So some metals, for example, things like iron, steel, cobalt, and nickel, are what we call magnetic, okay? So what that means is that a magnet will attract them. So for example, if you drop some steel pins on the floor, and you dropped quite a few steel pins on the floor, what you can actually do is use a magnet to pick them up. So if you had a bar magnet, for example, let's say, and you kind of hovered the bar magnet above the steel pins will actually be attracted towards that magnet, and it will all kind of go on the surface of this magnet, and you'll be able to pick them up. So there is a force that's basically attracting these steel pins onto that bar magnet, and that's called a magnetic force. Okay, this is an example of a non-contact force because it's acting over that distance. So you're actually hovering that magnet over and you're not touching it per se till that steel pin is attracted towards that bar magnet. So it's not coming in contact with the steel pins before there's that force acting on it. Okay, so this will be different from things like, say, friction, which is an example of a contact force, because friction is the resistance you have when two things are in contact with each other. So for example, if you were driving on a road and so this is my badly drawn car. okay, the wheels on that car is in contact with the road and it's creating a resistance, and that's what friction is. So this is an example of contact force, whereas with magnetic force, you're not directly touching that steel pin till it's being attracted towards um, that magnet and it's becoming in contact. So this is an example of a non-contact force. And the metals that are magnetic and the metals that are able to have this magnetic force acting on them is iron, steel, cobalt, and nickel. Okay, so these are examples of magnetic metals. So when you have a magnet and you leave that magnet for a while, what happens is that it has two ends, okay? So one end will always point to the north, okay? And we call that the north seeking pole, okay? That is the north seeking pole, and that's the one that's always pointed to the north. The other end will point to the south, and that is the south seeking pole. Okay, so a magnet always has a north-seeking pole and it always has a south-seeking pole. So you can figure that out by, if you just leave the magnet, you just hold the magnet and one side will always point to the north and then the other side will always be pointing to the south. And we will call that the north-seeking pole and the south-seeking pole of the magnet, okay? And these poles of so these ends of this magnet, so the north-seeking pole and the south-seeking pole, are important because if you go back to the iron fillings or the steel pins, the magnetic force in the steel pins or the iron fillings and other magnetic objects are always greatest when they're near the poles of a magnet, okay? So say, for example, let's go back to iron fillings, and you drop them on the floor and you're trying to pick them up with a bar magnet. So this bar magnet, always has the north seeking pole and the south seeking pole. So you can see that on this bar magnet here. Okay, so usually with bar magnets, especially the ones that you use on in the lab, the north seeking pole will be the red side and the south seeking pole will be the blue side. So there's a distinguished difference between the north seeking pole and the south seeking pole. Now, for example, say instead of being vertical, you used it horizontally and you were trying to pick up this bar magnet this way, it would be harder for you to pick up the steel pins because the greatest magnetic field is actually at the ends of the pole, okay? So it'd be easier for you to pick it up when it's vertical because the magnetic field is stronger at each ends. Okay, so if you're trying to pick it up this way, it would be harder for you to pick it up because the magnetic field will not be as strong. So each magnet has two poles which are equally as strong. So the north-seeking pole will be equally as strong as the south-seeking pole, okay? So when you hold two magnets close together, you find that the north-seeking pole, so if you had so that's one bar magnet. So you have the north-seeking pole there. Okay, so like things will repel each other and opposites will attract. Okay, so I'm sure you guys have heard this before. North and north will repel each other. So instead of them getting close together and getting stuck together, they will actually go opposite ways. Okay, so you can see that here you have two north-seeking poles, and instead of them being attracted, they're going the opposite way, they're being repelled. However, if you had a north-seeking pole and you pointed that towards a south-seeking pole, opposites in this north and the south will be attracted towards each other. So they will actually kind of join up. I'm sure you've seen magnets and they just kind of attract towards each other, okay? And so there's just three main points in this slide, okay? So the first is that the end, so each of these poles are where the magnetic field is strongest. Each poles are equally as strong, and north will repel. Yeah, I'm hoping that what we've said so far makes sense. Yes? Okay. So there is a magnetic field in the area around a magnet. So, okay. So there is a magnetic field in the area around a magnet. Okay. So in this area, a force acts on a magnetic object or another object. So if we go back to the magnet, if you go back to the bar magnet, you have a north and you have a south end, okay? There is a magnetic field around that magnet, okay? So in that area, the force acts on that magnetic object or another magnet. So for example, the magnetic field is either acting on those steel pins, which are magnetic, or they will be acting on another magnet. So if that field is strong, the force is big. Okay, so if that magnetic field is strong, the force is big. Then, i.e., you're able to, if you have a strong magnetic field around that bar magnet, you're able to pick up way more steel pins. Okay, if, however, the field is weak, the force is small. Okay, so you won't be able to pick up that many steel pins. And the direction of a magnetic field can be found using a small plotting compass, okay? The compass needle always points along the direction of the field, okay? So if you had a compass, the way it's pointed will always be in that direction of that magnetic field. So we can actually draw these magnetic fields out, and we can use magnetic field lines to represent a magnetic field. So there's just several rules you have to remember for magnetic field lines. And the first thing is that they always start from the north to the south, okay? So they always go in this direction. They always start at the north pole to the south pole. And when you have lines that are close together, that's where the field is the strongest, okay? If the lines are close together, you'll have the field that's where the field is strongest, i.e. the magnetic field is stronger there. So if you go back to the principle of picking up steel pins, you'll be able to pick up steel pins the most there. The further apart the lines are, the weaker the field is, okay? So a magnetic field is strongest at the pole. So if you think about this magnet, it will be the strongest here, because remember, at each ends of the pole, that's where the field is strong. And the further away you get from the poles, each end of the pole, you will the weaker the magnetic field is. So the magnetic field is strongest at the poles and of a magnet, and gets weaker as the distance from the magnet increases. So you can see the distance from these two lines will be, there's a better picture of this on the next slide, will be increasing because you're getting further and further away from each ends of the pole. Oh, sorry, each ends of the magnet, okay? And the really important thing I put in red is that these magnetic field lines are not actually real, but they're just a very useful theoretical model which will help us to understand magnetic fields, okay? So they're not, you won't actually be able to see them, but you can draw them to try and figure out where the magnetic field is and try to understand it, okay? Oh, okay, there we go. So this is an example of drawing the magnetic field. So you can see that you have your bar magnet. Okay, so there's your bar magnet there. You have your north seeking pole, you have your south seeking pole. So if you look at this plotting compass, you can see that the compass is pointing to the north, and this direction it's going to the south. So you know that this is your north seeking pole and this is your south pole of the magnet. You can also see that where it's closest to the poles, the magnetic field line is very close together. So do you see that's very close together? So you know that at that point, you have your strong magnetic field because it's the one that's closest, strong magnetic field. And that is the one that's closest to the, those lines are the closest to the north-seeking part of the pole, and that's where the magnetic field is stronger. But then if you get, say, around here, you can see these lines, as you go further from each pole, it's getting, the distance between each line is getting greater and greater. So you can see the further you go from that pole, it's getting bigger and bigger, okay? So at this point, you have a weak magnetic field, which makes sense because the further you go from each pole, the magnetic field is decreasing, okay? So at this part, you have in your weaker magnetic field, okay? And remember, the most important thing, these aren't actual real lines that you can see. This is just something that we can draw out as a model to try and understand magnetic field. Okay, so does that make sense? If it makes sense, can you put yes into the chat? Yes, okay, great. Let's move on then. So we kind of talked about compasses already. I'm just gonna have a look at how it works, okay? So a compass has a small bar magnet that can basically rotate. So you can kind of see that in the picture here. There is a bar magnet and that is constantly rotating. When a compass is held at rest in your hand, so when you're not moving it and you're just holding it at rest, the rotating magnet, because remember, it's a small bar magnet that it has, that rotating magnet will always settle in the north-south direction, okay? So it will go north, it will go south. And this thing is really important to remember because this behavior provides evidence for us that the Earth has a magnetic field, okay? Because we said magnets will point towards the north and it will go towards the south, okay? So it will go in this north-south direction. So it's providing evidence for us that the Earth has a magnetic field. The pole that is pointing towards the north, like we said, is your north-seeking pole, and the point that's pointing towards the south is your south-seeking pole. So like poles attract, this tells us that the magnetic, there is a south-seeking pole. So you remember the north and the two norths will repel each other. So since unlike poles attract, this tells us that at the magnetic north pole, there is a south-seeking pole as well. So we can use this idea that a magnet will point towards the north and then the other end of the magnet will point towards the south to prove that the Earth has a magnetic field, okay? So then let's do a quick question. So which of the following items will a bar magnet pick up? Which of the following items will a bar magnet pick up? What do we think? Okay, yes. And what else could it pick up? Yes. And there's one more that it could pick up. It wouldn't be able to pick up brass, but it would be able to pick up aluminium. Okay, so if we go back, so it will be able to pick up iron and steel, and those would be the two things that it would be able to pick up. So iron and steel. So Okay, so it'll be able to pick up iron and steel. Okay, so now we're going to be looking at permanent magnets. Oops. So we're going to be looking at the difference between permanent and induced magnetism. Okay, so we kind of covered the introduction on magnets. We're going to move on. So permanent magnets will produce their own magnetic field. Okay, so they will always have this own magnetic field. They will always have that north-seeking pole and their south-seeking pole. Okay, so with permanent magnets, you will always have that. How could you check to see if a magnet was permanent? How would you be able to check if a magnet was permanent? How would you be able to check? Any ideas? See if the magnet can repel. Okay, so you know that there's another magnet. So induced magnets can repel too. The way that you could check is by two permanent. The way you can check is by having two permanent. So one magnet that you know for definite is permanent, and if you have two permanent magnets, they will be attracted towards each other. Okay, so two permanent magnets, you have one magnet that is permanent and you get the other magnet, you get the magnet that you weren't sure, and see if they're attracted towards each other. You know a permanent magnet is a permanent magnet and not an induced magnet, because with induced magnets, it's a material that becomes magnetic when it's placed in a magnetic field. Okay, so induced magnets are temporary magnets. So with induced magnets, it will also always be attracted towards a permanent magnet. So the reason why this happens is because induced magnets is magnetized in the direction of this permanent magnet's field. So you'd be able to check if something is a permanent magnet or if it's an induced magnet is by having a permanent magnet. And if you took that permanent magnet away, is that magnet still magnetic, or is it not magnetic anymore? So if it's not magnetic anymore, then you know it's an induced magnet. But if it's still magnetic, then you know it's a permanent magnet, because you need a permanent magnet to make an induced magnet, basically, okay? Because that induced magnet is magnetized in the direction of that permanent magnet's field. Okay, so when the induced magnet is taken away from the permanent magnetic field, it will lose all or most of its magnetism quickly, okay? Which is why we say that induced magnets are temporary magnets, okay? So if you have an electric current in a conducting wire, so conducting wire basically, what do we mean by conducting wire actually? What do you think we mean by conducting wire? Let me just quickly look this out so I can draw better. Conducting wire. What is a conducting wire? Any ideas? What do we mean by conducting wire? In this scenario. Okay, so a conducting wire basically means that it can carry electricity, okay? It can conduct electricity. Okay, so it's made of a material that can carry electricity, and it can have electricity flowing through it, okay? So an electric current in a conducting wire will produce a magnetic field around that wire. So if you have a long straight wire carrying an electric current, and that's placed vertically, so up, straight up, so that it passes through a horizontal piece of cardboard. Okay, so we have the so we have the okay, so we have a piece of cardboard, okay, and you have a long straight wire carrying an electric current, and it's passing through a piece of cardboard, and you have iron fillings sprinkled onto the board. It can actually show you the shape of the magnetic field, proving that there is actually a magnetic field, because remember, iron is magnetic. Okay, so you have a conducting wire, it has electricity. So this is your conducting wire. It has electricity passing through it. Okay, so when you have a current that is small, okay, the magnetic field is too weak to notice. Okay, but when the large current is used, the iron fillings will show a circular magnetic field. Okay, so if it's small, the magnetic field is too weak. If a large current is used, a circular magnetic field pattern will show. So basically, it's saying that the amount of current you put in correlates to the magnetic field that you get. Okay, so it correlates to the strength of the magnetic field. Okay, so the magnetic field gets weaker the further away from the wire. So you can see that here, it's weaker here, whereas you have a lot of iron fillings around here. And if the current direction is reversed, so in this case, the current is flowing into the paper, okay? So it's flowing into the paper, so it's going downwards, okay? If it's going downwards, it will be in one direction. And if you had current going out of the paper, so going this way, so the current is flowing up, the magnetic field will be reversed. So how can we actually find the direction of the field? So how can we know if it's going clockwise or anti-clockwise? Not clockwise, sorry. If it's going clockwise or if it's going anti-clockwise, okay? But before we look at that, can we explain what is meant by a permanent magnet and then what is meant by an induced magnet? So quick question before we figure out how we can find the direction. What is meant by a permanent magnet first? So if you got a question in the exam which asked you about permanent magnets and give a definition for a permanent magnet, what would you put? What would you write? What is meant by a permanent magnet? Any ideas? What is meant by a permanent magnet? Excellent, well done. Permanent magnets produce their own magnetic field and they will always have a north and south pole. Very good. Okay, then what is meant by a induced magnet then? What is an induced magnet? What is an induced magnet? Any ideas? So you've got the definition for permanent magnets spot on. Okay, so permanent magnets produce their own magnetic field, and they have a north and south seeking pole. Okay, north pole and south pole, so they will always be magnetic. So that's your permanent. What would be the difference between induced magnet and permanent magnet? So how would you explain what is meant by a induced magnet then? It's just any ideas? How would you kind of write a definition for induced magnet? Should we have a look then? We're not quite sure. Okay, so an induced magnet gets magnetized from a permanent magnet's magnetic field, okay? So induced magnets are temporary magnets. So in our definition, we would say that induced magnets are temporary magnets, okay? They are temporary magnets. They are magnetized. They are magnetized. They are magnetized in the direction of the permanent magnet field, permanent magnet field. If you take the permanent magnet away, it will lose all of its magnetism. If you take the permanent magnet away, it will lose magnetism, okay? Lose its magnetism. So there's 3 points you kind of have to say. That permanent magnets are temporary, so they will be magnetized if you put them in a permanent magnet's magnetic field, and they'll be magnetized in the direction of that permanent magnet's field. And if you were to take that permanent magnet away, it will lose its magnetism. Okay, so there's 3 kind of points we have to remember for it. So there's the difference between permanent magnets and induced magnetism. Makes sense. Yeah, it makes sense. Come on, guys, if you can put your answers in the chat, it would be great. Okay, so I'm hoping so permanent and induced magnets make sense. Okay, right. So then let's go back to our current and thinking about what direction the current will be. What direction the magnetic field would be, if depending on what direction the current is going, and how we can find the direction of the field. So when the current is flowing into the paper, so this way, the field lines point in a clockwise direction, okay, around the wire. So the field lines will be, the magnetic field will be going this way, okay, so clockwise, okay. When the current flows out of the paper, so it's going up, okay, the field lines will be reversed and it will go anti-clockwise, okay? So it will go this way. So a quick way we can figure, so this is really important to remember, flows into the paper, so it's going down, will be clockwise, flows out of the paper, so it's flowing out, so going up, it will be anti-clockwise. So a really easy way to remember this is by using something called the right hand grip, okay? So the right hand grip rule will help you to remember this, okay? So, okay, so I want everyone to use their right hand and put it up into a thumbs up position, okay? So like you're giving someone a thumbs up. And your thumb, okay, your thumb of your right hand is going to be showing the direction of the current, okay? So in this case, your thumb is pointed up, okay? So it's pointed up, and the rest of your fingers, for the rest of your fingers, because you've obviously done a thumbs up position, your fingers will point in the direction of the magnetic field, okay? So your thumb is showing your current, so it's showing the direction of the current. So if it's pointing up, if you're doing a thumbs up, then obviously the current is going up. If you do a thumbs down, the current is going downwards, okay? So when you're doing thumbs up, it's going up. The rest of the finger is showing the direction of the magnetic field. So thumb, direction of current, the rest of the fingers showing the direction of the magnetic field. So if we look at this picture, okay, so if we look at this picture, the current is flowing up, okay? So it's flowing, so if you think about this example of it flowing into or out of the paper, this is flowing out of the paper, okay? So it's going up. Then if you do that, you can see, you can see that the rest of your fingers, it's going in the anti-clockwise direction, okay? So you can see your fingers are going this way, okay? So it's going this way. So it is anti-clockwise, okay? So when it's flowing out, i.e. when the current is going upwards, the direction of the magnetic field will be anti-clockwise, okay? Then if if the current was flowing into the paper, okay, so it's flowing in, so the current is going downwards, your fingers will be in the clockwise direction, okay? So when your current is, so the thumb obviously remembers your current, so it's flowing downwards, and then you have your the rest of the fingers showing the direction of the magnetic field. So in this case, when it's flowing into the paper, it will be going clockwise, it will be going this way. So it's showing that the direction of the magnetic field has reversed. So if you use the right hand grip rule, it can tell you, it's an easy way to remember, it'll be an easy way to remember what direction the magnetic field will be in relation to the direction of the current, okay? Does that make sense? Does the right hand grip make sense? So I want everyone to try it out, okay? So I want everyone to have a go at figuring out if it's going to be a right hand, if it's going to go clockwise, or if it's going to go anti-clockwise. So that's your piece of cardboard. Your current is going into the paper, so it's going this way. What will be the direction of these iron fillings? What direction of magnetic field will these iron fillings show? You plugged in the current and you have your wire, conducting wire, and it is going into the paper, so it's going in this direction. What would be the direction of your magnetic field? I want everyone to use the right hand grip, okay? So at home, you should all be doing either thumbs up or thumbs down, okay? And it should tell you the direction of the magnetic field. So in this case, if it's flowing into the paper or into the cardboard, what would be the direction of the magnetic field? So everyone use the right hand grip to figure that out. Once you've done that, write your answers into the chat box. Okay, so that's scenario 1. I'm going to do scenario 2. So you have your cardboard here, you have your conducting wire, you have your iron filings, okay? In this scenario, it's flowing, so this one is flowing out of the paper, this one it's flowing into the paper. Okay, so the current is going this way. So in this case, it's flowing out, so it's going this way. So the current is coming in and it's flowing out. In this way, in this scenario, the current is flowing into the paper. So out, into. So what direction would the magnetic field be? What do we think? Use the right hand grip to try and figure that out. We'll be going on our break soon. It's be the last thing that we do before we go on our break. Any ideas? Okay, so yeah, so the one is thumbs, so the right hand. So remember, don't use your left hand. You're always using, it's called the right hand grip. So yes, so the first one, the current is going up. Okay, so it's going out of the paper, so it's going up. So the direction, so number 2 is going into the paper. So when you do the right hand grip, it will be your thumb, you're doing a thumbs down position. Okay, so for number 1 then, because it's going out of the paper, okay, will it be clockwise or will it be anti-clockwise? So remember, thumbs up, so is it going clockwise or is it going anti-clockwise? What's the direction of the magnetic field? So what way would you see this kind of iron filings going? What way would you see it going? So you have the thumbs, the positions right, okay? So in the first one, it's going up. So what's the direction of the magnetic field? Remember, your fingers are showing you the direction of the magnetic field. So when it's going up, so it's going out of the, so the first one, okay, so if the first one, it's going out of the paper, so it's in a, the current is going upwards, your fingers are anti-clockwise, because imagine that is 12, okay, so on the clock, that's 12. Clockwise direction would be this way, anti-clockwise would be this way, wouldn't it? So when your thumbs are up, it's anti-clockwise, so your fingers are going around this way. And when it's thumbs down, if you imagine that's the 12 of the clock, okay, it's going clockwise. So thumbs up, anti-clockwise. So when it's going upwards, and so when it's going out of the paper, so upwards direction, it is clock. I'm hoping you guys can see my thumbs. So yeah, obviously it's going to be you have, and that's your, and it's going anti-clockwise, thumbs down, okay, that's still your 12 o'clock, but then it's pointing this way, so it's going this way, okay, thumbs up, anti-clockwise, flows out, so when it's going up, anti-clockwise, thumbs down, clockwise. Does that make sense? Does that make sense? the direction of the magnetic field? Yes, no? Yes, okay, great. Okay, so we're going to go on our break now till, what's the time? So it's 10:47 now. So till 11:03, we're going to be going on our break. Okay, so make sure, I will be questioning you on the right hand grip. So make sure to, on your break, just quickly go over it, okay? So I'll see you guys back at 11:03. Cool. Okay, everyone, so welcome back. Hopefully you can hear me okay. So before we move on, I just want to quickly review the right-hand grip. So if you have a conducting wire that has an electric current passing through it, and it was passing through a piece of cardboard, a piece of paper that had iron filings on it, you can work out the direction of the magnetic field, which we know directly correlates to the direction of the current. Okay, so we use the right-hand grip for that. So can anyone tell me what your thumb shows when you use the right-hand grip, and what does the rest of your fingers show? So when you put your hands up either in a thumbs up position or you put your hands in a thumbs down position, what is the thumb showing and what is the finger showing? So if you put your answers on in the chat. Okay. So what thumb is the direction of current. Excellent, well done. And your fingers are showing, what does your fingers show? Direction of the magnetic field. Excellent. So if the direction of current was up, what would be the direction of the magnetic field? The direction of the current was up, be the direction of the magnetic field. Would it be clockwise, anti-clockwise? Excellent, well done. And if the direction was going of the current was downwards, it would be clockwise. Excellent, very good. Okay, so then let's move on. Okay, so we already established that if you have a current going through a conducting wire, it will produce a magnetic field. So let's think, why is it producing that magnetic field? Okay, so this slide kind of provides an explanation for that. So the diagram shows a magnetic field that's produced when you have a current flowing through a long coil of wire or solenoid. So when you have solenoid, it's just basically a long coil of wire, okay? So this is your solenoid when you just have a long coil of wire, okay? So what happens is that this coil of wire actually will turn into and it will act like a long bar of magnet. Okay, so if it's acting like a long bar of magnet, it will have a north pole and a south pole. Okay, so it's creating that magnetic field. So let's just go through it again. You have a solenoid, which is your long coil of wire. You have your current, so this is showing your current, okay? So the current is going from positive to negative, so it's going in this direction, okay? Which is, sorry, let me rub it out so it's a bit more clear. So, oh, whoops. Okay. Okay, so you have your solenoid, okay? You have current, which is going in this direction, okay? So it's going positive, it's going all the way around to negative. And what we're saying is that it's creating this magnetic field. So this long coil of wire, the solenoid, has actually become like a magnetic, it has become like a long bar of magnet. Okay, so the magnetic field from each loop kind of adds on to the next one. Okay, so this solenoid is basically when it becomes magnetic when it has a current flowing through long coil of wire. Okay, so it becomes magnetic. So you would be able to pick up iron filings or steel pins with this solenoid. Okay, so this has become, well, whoops, this has become, well, whoops. So this has become what we would say an induced magnet. And this in particular is an example of an electromagnet, okay? It's an example of electromagnets. We'll look at this in more detail in future slides. Okay, so does that solenoid and it creating a magnetic field make sense? Okay, so then the question is, what can increase the strength of this magnet then? What are the things that could increase the strength of this magnet? What do we think? What could increase the strength of this magnet? So what could make that long coil of wire more magnetic, i.e. be able to pick up more ion filings? Add more cells. Okay, yes, so add more cells. So what do we mean by cells? What do we mean by cells? Any ideas? What do we think? Gives more energy. So by energy, you mean current, okay? So increasing the current would increase the magnetic field, yes, good. What else could you kind of manipulate in this experiment to try and increase the strength of the magnet? So one is increasing the current, good. What other things could you do? Think back to what this experiment involves, okay? So you have a coil of wire. Oh God, 1 second. So you have this long coil of wire, okay? So what could you maybe do to this wire that could increase the strength of the magnet? Add more wire, yes. Okay, so have more coils, good. And what about this sentence here? The magnetic field from each loop of the wire adds on to the next. So what could we kind of manipulate with this one, by using this idea? So you increase the current, you have more coil. Any ideas? What do we think? Have more loops, yes. Okay, so let's have a look then. Okay, so you could use a larger current, okay? We already discussed that. So if you have just more electricity going through, okay, it's going to obviously increase the magnetic field, isn't it? So you have a larger current, increase that kind of electricity, and it will increase the magnetic field. Okay, so it'd be a stronger magnet. If you use more turns, so remember if you're using more turns, okay, then that would also increase the magnetic field. Okay, so that would also increase the magnetic field. And another thing, if we go back, because the magnetic field from each loop is adding on to the next one. So if you're making it easier to kind of add on that magnetic field by having them closer together. So instead of it being really further apart, you put the coils really, really tightly and right next to each other, you're going to increase the magnetic field because there's less distance for the magnetic field to kind of add on to the next. So you increase the magnetic field. And then one last thing that will increase the magnetic field is by putting an iron core in the middle of the solenoid. So you have the iron core and you kind of put the long coil of wire around the iron core. These four things, so using a larger current, using more turns of the wire, putting the turns closer together and using an iron core will all increase the strength of the magnetic field produced by the solenoid, okay? So 4 factors. So by doing this, you're actually creating something called an electromagnet, okay? So you create this electromagnet by they're made into that two strong magnets by having two coils with many turns of wire. So you can see all this wire with loads of coil here. You have the coil being very, very close together, and you increase that magnetizing effect of the current. Okay, so you've turned, so there's a current being supplied, so you're providing that electricity. You have that coil that's turned very, very close, and you have a lot of that turns, and you create this very strong magnet that we call an electromagnet. So when that current is switched on, so obviously current is going to pass through, and it's going to turn this into an electromagnet, okay? And you will be able to pick up all these iron filings. So do you see the amount of iron filings? It's a lot of iron filings it's able to pick up, right? So what does that mean? It's you are using a big current, okay? Using a big current. So you're able to pick up a lot of stuff. It's a very strong electromagnet. So when you have the current passing through, it becomes magnetized, and you're able to pick up all these iron filings. So, but when you switch it off, the magnet loses its magnetism. Okay, so remember, it's an induced magnet. It's an induced magnet, and it's a temporary magnet. So the iron filings will fall off. So if you don't have a current passing through, you no longer have a magnetic field. You need that current passing through that solenoid for it to produce a magnetic field. Okay, can anyone think of a way in real life where they use this principle, where they use this principle of electromagnet? Can anyone think of an example in real life where they use principle of an electromagnet? So they have this loads of wires, so loads of turns of this solenoid, okay, so long coils of wire, and they have a current passing through, and it's able to pick up. So someone said trains. So electrical trains, yes. That wasn't exactly the example that I was thinking of, but that is one example. Think of it in terms of the picking up things. What do we think? If we wanted to pick up heavy things, right? If we wanted to pick up heavy things, we wanted to pick it up, and then we wanted to kind of drop it off. Maybe think with cars, maybe. So the example that I was thinking of with electromagnets is when you have those, when you would go to places where they like, if you had an accident and your car was about to be scraped off, and you kind of put it into maybe landfills or things like that, where they would where your cars would go and your car can no longer be used. They would use the principle of so they would use this principle of electromagnet. So you'd have this towing situation, okay, and you would have your car here. Someone would sit in this bit, and they would turn on the electricity, okay. So then this so this is your car, okay, that needs to be basically dropped off, and you can no longer be used. So this car is basically going to waste, okay. So you would turn on the electricity, and so you would have current passing through. So this would have two iron cores and have loads of, you'd have a solenoid, so you would have long coils of wire, so you would have loads and loads of it, okay? So when electricity passes through, this becomes an electromagnet, okay? So it becomes an electromagnet. This part of the system will become an electromagnet, and you would be able to be attracted, which is obviously made of metals, okay? So you would able to pick up your car, and they would be able to pick up the car, and then where they need to drop it off, they would have the waste fills, okay? They would pick up the car, and they would turn off the electricity so that this is no longer magnetic. So when they turn it off, they'll be able to drop it in wherever they want to drop it off, okay? So the idea that you can turn on and turn off something for it to be either magnetic or not magnetic can be used in a lot of places where you need to pick things up, so heavy things. So they would turn off the electricity, so there's an electric current passing through it. The bottom bit would become magnetic, and so you'd be able to pick up your car. It would have to be a very, very strong magnet, and then they would turn off the electricity. So this part is no longer magnetic, so the car would drop. Okay, that's an example of where they use they would use the concept of electromagnets. Does that make sense? Yes? Does that make sense? Yes? No? Yes. Okay. Okay, then let's do 2 questions. So first of all, list 4 ways to increase the strength of an electromagnet. So what are the 4 ways that we talked about to increase the strength of an electromagnet? This is, so top tip, this is a question that they like to ask quite a lot in exams, okay? And they like to ask questions where with experiments, you manipulate each factor. So by manipulate, I just mean you change each factor and see how that has an effect on the strength of the electromagnet. So you need to have this 4 ways of increasing the strength of an electromagnet memorized in your head. So what are the 4 ways that you can increase the strength of the electromagnet? So we have 1, use a larger current. Yes, good. Use more loops. Excellent, well done. 2 more. So then can someone else give me the 2 more? What are the 2 other ways you can increase the strength of an electromagnet? Putting the loops closer together. Excellent, well done. What's the last way? What's the last way that we can increase the strength of an electromagnet? What do you think? What was one last way we talked about? Any ideas? Okay, so the last thing that we talked about was putting an iron core in the middle. So you have the iron core, and then you do your loops of wire around this iron core, and that would also increase the strength of the magnetic field, okay? So with the electromagnets, what you will find is that you have, and it will have many turns of the coil wire around that iron core. Okay, so those are the four things. You use a larger current, you use more coil, you do the coil, so you do more turns, not just use more coils, you have to be more specific. So you use more turns of coil, you put those turns closer together, and you use an iron core. Okay, so the wire that we use has to be insulated wire. Okay, so why must you use an insulated wire to make an electromagnet? Why do you think you must use an insulated wire to make an electromagnet? What do you think? Any ideas? Why must you use an insulated wire? So this is a much harder question. So if anyone gets this, they'll be very impressed. Take a guess. Why might you use an insulated wire? So think about maybe the amount of current that you might use. Any ideas? What do we think? Okay, so we have to use an insulated wire to make an electromagnet because there's a risk of it. There's a risk of it forming something called short circuit. Okay, so it's it's safer to use an insulated wire because if it turns into the short circuit, there is a risk of a fire, or if it getting really, really hot. Okay, this is one of the dangers of electromagnets. So we use something insulated wires to make it safer. So short circuit, what we mean by it becoming into a short circuit is that it basically you have the circuit going into a path of least resistance. Okay, so it goes into least resistance. So you have a lot of current that this wires can actually take going into these wires, and that can force things like fires and heat. So we have to insulate these wires to make it safer, basically. Okay, cool, right, moving on then. Okay, so a car starter motor needs a very large current of about 100 A to make it turn. So switching large currents on and off needs a special heavy duty switch. So if you had a large switch inside the car, it'd be nuisance and it would take up a lot of space as well. Okay, the switch would spark and it would be very unpleasant and it would be dangerous. So a way around this problem is by using something called a relay. Okay, so with cars you need to turn it on, okay, and that requires a lot of current. And so if something requires that much current, you would need a very heavy switch. Okay, so if you had that very heavy switch inside the car, that would just take up a load of space and it would just be a dangerous thing to have. So we use a system called a relay. Okay, so inside the relay, a solenoid is wound around an iron core. Okay, so you have an iron core and you have the long coil of wire and you have those many turns. Okay, so what does this become then? What does this then become? What do you think? So when the car is ignited, so when the car ignition is turned, a small current magnetizes the solenoid and its iron core. Okay, so you turn the switch on. Okay, so imagine you're in your car, okay, and you turn the switch on, and in the front of the car, you have your iron core with your solenoid. So a small current has passed from when you turn the car into that solenoid and its iron core. So this solenoid and its iron core now therefore becomes what? What does it become? What do you think it becomes? So once you turn your car ignition on, a current, so electric current is passing from the inside of the car and it's passing to that iron core. And with the iron core that has long coils of wire. So what does that now become? Any ideas? So we looked at it just before. We talked about the concept just before. What do we think? Okay, so if a current is passing through a through an iron core that has a solenoid on it, now that becomes an electromagnet. So what does that mean? It just has a magnetic field. So it becomes an electromagnet and it has a magnetic field. Okay, so there's a magnetic field around that now. So that solenoid is now attracted towards another heavy duty electric contacts, which is also made of iron. So remember, iron is magnetic. So this is now creating a magnetic field, which is now attracted towards that heavy duty battery. So what happens is current can now flow from the battery to the starter motor. Okay, so this is another example of how the electromagnet is working. Okay, so you turn the car ignition, it sends a small electric current to an iron core that has a solenoid wound around it. That is now being turned into an electromagnet. It's producing a magnetic field, which is then attracted towards a heavy duty electric contact, which is also made of iron. So this is also magnetic. And then a current is flowing from that heavy duty electrical contact from the battery into the starter motor. So this system will allow the car engine to be started by turning a key or pressing a switch at a safe distance. So we don't have to come out and turn on this switch every time, okay? Because there's a relay happening between here and we're producing a magnetic field here, okay? So this is where the magnetic field is happening so that the switch is being then turned on because there's the current going from that battery to the starter motor. So the car now can be turned on, okay? Does that make sense? Yes? Does that process make sense? I'm hoping it makes sense. Can I get some yeses in the chat if it's making sense, please? Yes? Do you want me to explain it again, or is that okay? What do we think? So the electromagnet is helping the process and it's making it more kind of convenient for us. Make sense? Come on, guys. Okay, so I'm hoping that makes sense. We're going to move on now. Okay. Right, moving on. Okay, so we represent magnetic fields by drawing lines that show the direction of the force on a north pole. Okay, so these lines are magnetic flux. So the lines in B, if we look at this, so the lines in B are stronger than the lines in A. sorry, the magnets in B are stronger than the magnets in A. So this means that they will exert a stronger attractive force on a magnetic material such as an iron nail. So we kind of already looked at this principle, okay? So we know that these are magnet B is stronger than magnet A, because if you look at the magnetic flux, okay, so magnetic field lines, we called them earlier, so we can call them magnetic flux, they are way closer together. So you have the magnetic field lines going from north to south, and then there's an attraction between north to south as well. So there is a magnetic field here, okay? And the magnetic field is stronger here because these magnetic flux lines, so the magnetic force, okay, so the magnetic force is stronger with with this, because these lines are closer together. So if you draw the magnetic flux lines closer together, you're showing that the magnets are stronger, okay? So we can figure out the strength of the magnetic force using this equation, okay? The equation is force equals magnetic flux density times by current times by length, okay? So let's look at this example. The strength of the magnetic force is determined by the flux density. So in a laboratory bar magnet, it produces a flux density about 0.1 Tesla near to its poles, okay? So the force, with every equation, we need to know the unit. So the force is in newtons, okay? The magnetic flux density will be in something called Tesla, so T, okay? So that's here. The current will be in amperes, so that will have a symbol A, and the length is in meters, which is m. Okay, so if it was in centimeters, we'll have to convert it into meters. Okay, so let's look at this example then. A wire carries a current of 3.0 amperes. Okay, and calculate this force acting on this wire. Okay, so force equals, remember BIL, so B represents magnetic. So it represents magnetic flux density. I is your current. Okay, so I is your current, and then L is length in meters. So how would you work out the magnetic force acting on this wire? How would you work out the magnetic force that's acting on this wire using this equation? So that's quite simple. You would just plug the numbers in. So B is 0.2 times by I, so it's already shown us that it's 3.0 amperes, times by the length, which is 0.15. And that should tell us the magnetic force. So if we all get our calculators out, and we put it in 0.2, whoops, let's turn the calculator on. So 0.2 times 3 times 0.15, it tells us that we have magnetic force is 0.09 newtons. Okay, so this equation is actually one of the easier equations to use in physics. You just have to remember that it's magnetic flux density, which they will usually give it to you in a question, times by the current, times by the length. Obviously, they could ask these questions the other way around, in the sense that tell you the force, they tell you the current, they tell you the length, and you have to work out the magnetic flux density. You just rearrange the question. So you just rearrange the formula. Okay, so so how would you rearrange it? So if they gave you the force, they gave you the current, but they wanted, and they gave you the length. Okay, how would you work out, what formula would you use to work out magnetic flux density? What formula would you use? How would you rearrange the formula to try and work out magnetic flux density? Because they could kind of give you several parts of the equation and try and get you to work out one of the parts. How would you rearrange the formula? Any ideas? What do you think? This is just rearranging the formula. Yeah, excellent, well done. So you just move this to the side. Okay, so it's force over current times by the length. Okay, so it's just a matter of remembering the formula. Okay, right, next. Okay, so let's have a go at answering this question then. So the wire of length has 0.2 meters placed at right angles to the region with a magnetic flux of 2 Tesla and the current of 4.5 amperes is passing through the wire. So calculate the force. Okay. First of all, I want you to tell me, so let's work through it in steps, okay? So first of all, I want you to tell me the formula you would use. Yeah, so what formula would you use to try and work out this question? What formula would you use, guys? So force equals what? What does force equals? Force equals so force equals, it's the formula that we talked about just now. Force equals magnetic flux density times by current times by length. Okay, so that's the formula. So what would be the answer to this question? So I want everyone to have a go at trying answering this question. What would be the answer to this question? What would be the force acting on the wire? What do you think? So we just need to substitute in the values. Okay, so we have one answer in. So can you tell me what number? So can you tell me what you put into your calculator? So I want to see. Okay. Yes, so you just do magnetic flux density, which they've told you is 2, times by the current, which is 4.5, okay, times by the length, which is 0.2. So first you would have to make sure that it's in meters, because remember, you always have to remember your units. So it's in meters. So we'll put that into the calculator. 2 times 4.5 times the length. Excellent, well done. So that would give you 1.8. Okay, so does everyone understand how to work out magnetic force. Does everyone understand the equation? If so, can you put yes into the chat? Yes? Okay, moving on then. So this is going to be the last thing that we do before we go on our break. Sort these sentences into the correct order to explain how the relay operates to connect the car starter motor to the battery. So I want you to put this into the correct order. So if you just write into the chat what the order would be. So would it be A, B, C, D, E, A, B, C, D? What's the order? So explain how the relay operates. So have a read and try and figure it out. So it'll be the last thing that we do, and we're going to go on a lunch break from after this question. We'll be going on our lunch break. You guys are doing really well. This is a bit of a hard topic, so guys are doing really, really good. So what do we think? What's the order in how the relay system works? Any ideas? What are we thinking? Give you guys one more minute to think about it. Sorry, 30 more seconds. Okay, so what would be the first thing that you need to do? A, excellent, good. Then what would happen? So the ignition switch is turned, and then what would you do? Not quite. So when you turn the ignition switch, what happens? C, good. Not quite. So what has to happen before the iron core becomes magnetized? So the current has to pass through first, doesn't it? So A, the ignition switch is turned, current flows through the solenoid. So that's what the current is making the iron core become magnetized, isn't it? So the current passes through the iron core, becomes an electromagnet, i.e. becomes magnetized. Okay. Then when it becomes magnetized, it connects to the contacts. So the solenoid moves to the contacts, that's E. And the motor is connected to the battery, which is going to switch the battery on, isn't it? So B. So it goes A, D, C, E, B. The ignition switch is turned on, the current flows through the solenoid, the iron core becomes magnetized, the solenoid moves to connect. So because this is now magnetized, the contacts are also made up of your iron core. So it moves to connect to the contacts, because now the iron core is magnetized. So the solenoid is magnetized, so it's going to be attracted towards the contacts, and the motor will be connected to the battery. Okay? Okay, does that make sense? Okay, so we're now going to go on a half-an-hour break. Let's see, there's something. Yes, okay, good. So now we're going to go on a half-an-hour break. So from till 17 past 12. Okay? Okay, I'll see you guys after the break. Okay, everyone. So, welcome back. So we're just going to carry on. Okay. So, so on this diagram, you can see a piece of aluminium. Okay, so there's your piece of aluminium foil between two poles of strong magnets. So there's your magnet 1 and there's magnet 2. Okay, you have this aluminium foil going through this strong these two strong magnets, and a current through the foil has caused. So you can see there's a current here, and it's so the current is being the current is going through. The current through the foil has caused it to be pushed down away from the poles. Okay, so you have your aluminium foil, you have two strong magnets. You have your two strong magnets pushing. You have your two strong magnets, and the current is passing through this foil, and this current passing through the foil has caused this foil to be pushed down. Okay, and so if the current was reversed, so instead of going this way, it went this way, the opposite way, the foil would move upwards, again, away from the poles of the magnet. And we call this the motor effect. And it happens because of the interaction between the two magnetic fields. So the two magnetic fields that we have is this one, which would be your permanent magnet, okay? And then you have your aluminium foil, which, because it has a current passing through it, has now also become magnetic. And that's your electromagnet, okay? So one produced by the current in the foil, so this one, and then this permanent magnet. So the interaction between two has caused the foil to either go up or down, depending on the direction of the current, okay? So let's look at that in a bit more detail. So by itself, the field between the two poles of the magnet, so you have your north pole and your south seeking pole of the magnet, between the two poles of the magnet would be constant strength and direction. So you can see that magnetic flux density lines here, okay? The current around the foil is producing a circular magnetic field. So this is your foil, aluminium foil, and you have your circular magnet, okay? And it's producing a circular magnetic field. So in one direction, the magnetic field from the current squashes the field between the poles of the magnet. So it's basically squashing it. And so because you have a magnetic field like this, and then you have the circular magnet, so it's squashing that magnetic field around the foil. And it's the squashing of the field that produces a force on the foil upwards in this case. Okay? So we can use another rule to basically try and figure out whether the force would be upwards, okay, or whoops, why is this not working now? Yeah, so we can basically use another rule to try and figure out if the force would be upwards or downwards. And that is what we call Fleming's left-hand rule. Okay, so the size of the force acting on the foil, so we will look at the Fleming's left-hand rule in a bit more detail, but before we do that, the size of the force acting on the foil depends on these three things, okay? So it depends on the magnetic flux density between the two poles, okay? So basically how strong those two magnets are. So we have one magnet, two magnets, so there's north pole, south pole. So what are the magnetic flux? So are they like this, or are they stronger magnets and the flux density magnetic flux is closer together? So how strong the magnets are, the size of the current, and the length of the foil between the two poles. So is it very close together, or, sorry, is it further apart, or is it close together? So the length. So this relates. So changing these three factors can change the size of the force acting on the foil. So this relates back to an equation. Okay, so what equation does this relate back to? What do we think? What equation that we looked at earlier does this relate back to? Excellent, well done. Force equals basically Bill. So magnetic flux density times by the current times by the length, doesn't it? Okay, so then let's look at Fleming's left-hand rule then. So Fleming's left-hand rule, we use 3 fingers. I'm hoping, yeah, so we use 3 fingers. Okay, so we use our thumb, your first finger, and your second finger. Okay, so what we use this Fleming's left-hand rule is to try and figure out if the force, so when you have 2 magnets and you have a current passing through those 2 magnets, we use the Fleming's left-hand rule to see whether the force would be upwards or the force would be downwards. So your thumb, so let's go on to, okay, so like I said, we use the Fleming's left-hand rule. So what you're going to do is spread your first 2 fingers, okay? Spread out the first 2 fingers and the thumb of your left hand, so they are right angles. So this part is really important. Your thumb and your second finger should be at right angles to each other, okay? Let your first finger point in the direction of the magnetic field, okay? So the first finger, this finger, okay, should be in the direction of the magnetic field. So this finger represents the magnetic field. The magnetic field is going to go from north to south. Okay, so it's going to go north to south. Your second finger points in the direction of the current. Okay, so the points in the direction of the electric current. So it's going to go from positive to negative. Okay, that should determine where your thumb is. So your thumb then points in the direction that the wire is moving, i.e. where the force is. So is it going up or is it going down? Okay, so then let's go back and look at this with this example on this slide. Okay, so if you all get your fingers out, if you all get your hand out, okay, and we're going to apply those 3 rules, okay? So your first finger, i.e. this finger, okay, we said, so you can remember it, so first finger, you can remember is the field, magnetic field, so they both start with an F. So what do we say? So what direction would that go? Would it go south to north, or would it go north to south? So is it going north to south, or is it going south to north? The magnetic field. What do we think? Any ideas? What do we say? What direction does it go? Okay, so it's going to north to south, okay? So the magnetic field is always going to go from north to south. So your finger will be pointing in this direction. So your first finger will be pointing in this direction because that's where the north is. So in this diagram, in this example, that's where the north is. So the north will be here, south is here. So it's pointing in this direction, okay? Now, the current, okay, is going this way. So if you look very closely, you can see the arrows on this one, okay? So the current is pointing this way. Okay, so your thumb, your second finger is showing the direction of the current. So you can remember that as second has C in it, so does current. Okay? So naturally your thumb will be pointing upwards. So the force is up. So the movement of the foil with the current passing through it would be up. Okay? Does that make sense? So your first finger shows you the field, second finger shows you the current. You remember it because first has F in it, so field. Second has C in it, so that's the current. And then your thumb, you remember, is the movement. So it's either up or down. So it's the force either going up or the force going down. Okay? Right. So does that make sense? Do you guys, does the whole principle of Fleming's left-hand rule make sense? If so, can you put yes in the chat? Yes, no? Do you want me to go through it again? If you could put something in the chat, that would be great. Yes? No? Okay, so I'm hoping that makes sense. Okay, right. So let's kind of switch things up and see how, and try and use the left-hand rule to try and work out where the force would be, whether it would be up or down, okay? So in this example, we said that it's going up. So we're going to look at a different example where instead of it, sorry, just get the pen. Okay, so this, we're going to change. This is no longer south. This is now north. This is no longer north, and this is south. Okay, so we've changed the direction of the magnetic field. So this is now the north seeking pole, and that's the south seeking pole. Okay, so what direction now would the current flow in? Sorry, what direction would the force go? So is it up or down? So we've changed the magnetic, so we've changed the each end of the pole. Would it still point it up? So can we try and use the Fleming's left-hand rule to try and figure that out? What do we think? Any ideas? Come on, guys. There's only 2 of you in this lesson, so I would appreciate some contribution. So can we try and use the Fleming's rule to try and figure out, would the force will still be going up or would it go down? Would the movement be up or would it be down if we changed this magnet to the north and then this magnet to the south? Can you guys hear me okay? Okay, so let's have a look then. So your first finger, okay, so your first finger, sorry. Okay, right, so let's have a look then. So we said that first finger is pointing, okay, so the first finger is going, it's not going in this direction anymore, it's going the opposite direction. So first finger is showing the direction of the magnetic field, so it's going from north to south, okay? So that makes sense, doesn't it? North to south, okay? Your current is still going in this direction, isn't it? Okay, so your current is going this way still, okay? It's going this way. So now the force movement would be downwards, wouldn't it? I'm hoping you guys can see this. Can you see it? Okay, so yes, I'm hoping you can see it. Okay, so magnetic, so the first finger showing the magnetic field is now going from north to south. Your current is still flowing the same direction, so it's still going this way. But now that means your thumb is pointing downwards, hence the force movement would be down, okay? Does that make sense? So changing the poles will change the direction in which the current is flowing. Sorry, the direction in which the movement is going, so whether it's going up or down. Similarly, changing the current would also change the direction of the thumb. Okay, so it also changed the movement, whether it's going up or down. So instead of it going this way, if it was going the opposite way, what would happen to the movement of the thumb? So what would happen to the force? Would it move the foil up or would it move it down? So instead of going this way, it's going this way now. So we're going to turn it back and go back to the original in terms of the poles of the magnet. So we're going to turn this back. So, okay, so this time we're changing the direction of the current. Okay, so if we change the direction of the current from going, so let's rub all this out, you guys can see it properly. So if we're going to change the current from going from this way to back this way, so the direction of the current has reversed, what would happen to the movement of the foil? Would it go up or would it go down? What do you think? Okay, let's try and figure it out. Okay, so we have the first finger showing, so the first finger is showing us the current. Okay, so it's going from north to south. Okay, so sorry, the first finger is showing us the field. Okay, so the first finger is showing us the field. It's going north to south. Okay, so this is north end going to south, so it's pointing this way. Then the current, instead of it going like this, so sorry, I'm not putting, instead of going like this, it's going the opposite way, isn't it? So it's going this way now, isn't it? Okay, so it's going this way. So naturally, the thumb would point downwards, hence the direction of the foil would move down. Okay, so do you see how reversing the current and reversing the pole, so reversing the current and reversing the poles changes the direction of movement. So it changes whether the foil goes up or whether the foil goes down. Okay, does the Fleming's left-hand rule make sense? We getting it? So the things you just have to remember is that should just remember what each finger is representing. So first finger represents magnetic field, second finger represents the current, and the thumb is representing the movement. Okay, then the next thing to just remember is that magnetic field always goes from north to south, and the current goes from positive to negative. So in this case, this end, so in this direction, that's positive to negative. This direction, that's positive to negative. So the direction of current has reversed. Okay, so I'm hoping that makes sense. Should we move on? Okay, moving on. Oh, whoops. Okay. Right, next then. Okay, so this, oops. So this diagram shows a coil of wire that's able to rotate around an axle. Okay, so there is an axle here, that's your axle, and there's a loop of wire that's rotating. So this is a positive, it's negative. Okay, when the current flows as shown in the diagram, so when it's going this way, so it's positive to negative. There is a downward force on CD and an upward force on AB. So the coil will begin to rotate anti-clockwise, but the coil will rotate no further than the vertical position. Okay, so how is that working then? So if it's going positive to negative, we can use the Fleming's left-hand rule to try and figure out what direction it would go in. So C to D, okay? So it's going positive to negative. So we remember that the first finger is your direction of the magnetic field. So it's going north to south. Okay, so it's going this way. And then the current is going positive to negative in this direction, isn't it? So positive to negative. Okay, so the current is going this way. So naturally, C and D would go downwards because it's this way, because the thumb is pointing down. Okay. A to B, on the other hand, the current will be flowing in the opposite direction. So it'd be going this way. So then A to B would go upwards. Okay, so it will begin to rotate anti-clockwise. So it'll go this way. Sorry, it'll go this way. Okay, but the coil will rotate no further than vertical position. So how can we try and get it to rotate all the way around? So the coil is kept rotating by using a split ring commutator, which rotates the coil between the carbon brush contacts. Okay, so you have your carbon brush contacts here. Okay, so here and here. And it's kept rotating using this split ring commutator, okay? As the coil passes the vertical position, the two halves of the commutator change contact from one carbon brush to the other. So this is causing a direction of the current in the coil to reverse. So this basically reverses the direction of the current, okay? So in this case, where you just have it going this way, so the current is just going this, it will just go like that. So because the movement is downwards, okay? So A to B would go up, and then C to D is going to go downwards. The direction of current is here. But then it's not going to, but then A to B isn't going to be able to go further up because the current isn't able to switch. So you use a split ring commutator to try and get it to switch, to try and reverse the direction of the current. Okay, so use a split ring commutator because it reverses the direction of the current. So when it reverses the direction of the current, you're able for it to spin 360 degrees. So the coil will continue to rotate clockwise as long as there is a current. Okay. So when conducting wire passes through a magnetic field, a potential difference is produced across the ends of the wire. Okay, so when a conducting wire moves through the magnetic field, a potential difference is produced across the ends of the wire. A potential difference produced in this way is described as an induced potential difference. Okay, a potential difference will also be induced if there is a change in the magnetic field around a stationary conducting wire. So that's really important to remember. A potential difference will also be induced if there is a change in the magnetic field around a stationary conducting wire. If the wire is a part of a complete circuit, the potential difference will cause a current in that circuit. And this is called an induced current. Okay? So changing the direction of motion of that conducting wire, so you can see it here, or changing the polarity of the magnetic field, so changing it from north to south or south to north, will change the direction of the induced potential difference and reverse the direction of the induced current. So there will need to be a change in the magnetic field. And inducing a potential difference or a current in this way is called a generator effect because that's how we generate electricity. Okay? Okay, so we can also induce a potential difference in a coil of wire by changing a magnetic field near it. So we can change that direction of that current by changing the magnetic field. So when you have a north pole, so you have your solenoid with your long coil of wire here, and you have current passing through it. So now this is So now this is magnetic. Okay, so then you have your north pole here. A north pole of a magnet is pushed into the solenoid. Note that the induced current flows in a direction that makes the solenoid next to the magnet also behave like a north pole. Okay, so this also becomes a north pole when when the north pole of one magnet is being pushed in, and you have a solenoid where there's a current going through it, and it's also now become electromagnet. This now acts as a north pole. When the magnet is pulled out of the solenoid, that direction of the induced current is now reversed. So now the end, this bit behaves like a south pole. So when you push it in, the current is going this way. Therefore, this end is acting like a north pole. So when it moves out, okay, it is going to act like a south pole. Okay. So when it's being pushed in, a north will repel. Okay. When it's being pushed out, you have a south pole. So you can see then the direction of current has now reversed. So instead of it going from this way, it has now come this way. So the north and south pole will attract. Okay. Okay, so the challenge question then. A wire is made to move through a magnetic field. So it's supposed to say magnetic field. So that potential difference is induced across its ends. State 2 ways in which the induced potential difference can be increased. What do we think? What are 2 ways you can try and increase the size of the induced potential difference? What do you think? Any ideas? Any ideas? Maybe not necessarily increasing the current, but what can you increase? Sorry. Yes, so wait, sorry, yes. So increasing the current, yes. So, or what's the other thing that you could do? Maybe something with the wire. What else could you do with the wire? What could you do with the wire that would help? Any ideas? So you could do more turns around the wire. So similar principle as to what we looked at in electromagnets. You could do more turns. We could use a higher current, things like that. Okay. So moving on then. When a current is induced in conducting wire, the induced current itself generates a magnetic field. Okay. The magnetic field opposes whatever. Okay, so the magnetic field opposes whatever the original change was that caused it. So this may be the movement of the conducting wire or the change in the magnetic field. In each case, as the magnet is moved, a current induced, there is a force which opposes the movement of the magnet. So when you move a magnet to induce a current, you do work. Okay, so When a current is induced into a conducting wire, the induced current itself generates a magnetic field. So induced current is actually producing magnetic field itself. The magnetic field will oppose whatever the original change was. This may be the movement of the conducting wire or the change in the magnetic field. In each case, as the magnet is moved and a current induced, there's a force which opposes the movement. When you move a magnet to induce a current, you're doing work. Okay, so let's look at electromagnetic flow meters. Okay. Oops. Okay. So electromagnetic flow meter. So you have a flow meter. A flow meter is a way to measure the rate of flow of oil through an oil pipeline. So that's what a flow meter does. Okay, so it measures the rate of flow of oil through an oil pipeline. So you have a small turbine placed in the pipe. Okay, so there's your small turbine placed in the pipe so that you have oil flowing through it. So when the oil flows through it, it's going to turn these blades. So this is going to turn these blades, okay? So then you have some magnets that's placed in the rim of the turbine. Okay, so they move past a solenoid. Okay, these moving magnets can actually produce a potential difference in the solenoid. Okay, and then that potential difference can be measured on something called an oscilloscope. And the faster that turbine is rotating, the larger the potential difference induced in the solenoid. So by measuring this potential difference, an engineer can tell you what rate the oil is flowing at. Okay, so let's go through that slowly again. You have turbine, okay. So the reason why we're doing the flow meter is we want to measure the rate of flow of oil through an oil pipeline. Okay, so you have oil passing through. You have because as the oil is passing through, it's turning that blade. Okay, it's turning that blade, and then you have magnets. Okay, placed at either rim of the turbine. So they move past that solenoid, okay? These moving magnets can induce a potential difference in that solenoid. So as these magnets are moving, it's producing an potential difference in those solenoids, okay? So remember, solenoids are a long coil of wire that has electricity passing through it. Long coil of tons of wire, okay? And that potential difference can be measured on an oscilloscope. So we're going to look at that later. So if the turbine is rotating faster, it's going to produce a larger potential difference in the solenoid. And we can measure that, we can look at that potential difference to see the rate at which the oil is flowing. Okay? So that's what this is. So this is an oscilloscope. So this diagram shows how an induced potential varies within the time. And this waveform can be displayed on an oscilloscope, okay? So this diagram shows a design of a simple electricity generator. This one generates alternating current, and this is called an alternator. So by turning the axle, you can make the coil rotate in a magnetic field, and this is causing a potential difference to be induced between the ends of the coil, okay? Oh, no, okay. So yeah, so this is showing us how simple electricity is generated. You have alternating, so it's called an alternator because it has all AC current, AC. By turning so you see the axle, you can make the coil kind of rotate, and you have this magnetic field here because there's a north pole. You'll be able to, if you wanted to draw these magnetic, sorry. Okay, so Yeah, so you can see that it can rotate in our magnetic field because there's a north pole here and south pole here. You'll be able to show your magnetic flux dense lines if you wanted to. So this is causing the potential difference to be induced between the ends of the coil. Okay. So this diagram here, okay, shows the position of the coil at the times marked on the oscilloscope. So the coil is vertical. In this position, sides AB and CD are moving parallel to the field and no potential difference is induced. So if we look here, AB and CD are parallel. So when the coil is vertical, it's parallel, okay? AB and CD are parallel. So when they're parallel, there's going to be no potential difference. Okay, so when it's like this, when both sides are like this, it's not going to induce a potential difference. So that's vertical. So then when it spins to horizontal, okay, so sides AB and CD are horizontal. So the coil is horizontal and the positions AB and CD will be cutting through the field at the greatest rate, okay? And that induced potential will be at its maximum, okay? So it will go vertical, horizontal, and that's when they will be at cutting through the field at a greatest rate, okay? And then it will go vertical again. So I'm hoping you guys can see this, go vertical again. So when it's parallel again, there'll be no induced potential, okay? So there'll be no induced potential difference. And then it will go horizontal again. When this goes horizontal again, obviously A and B will be moving in opposite direction in comparison with position IE. So when it was horizontal, so we've got vertical, horizontal, vertical, and I'm not really able to show it with this hand, but it will be horizontal again. So it'll be same as this, but the opposite direction. Okay. So induced potential difference is again at its maximum, but now in the opposite direction. Okay. And the size of the induced potential difference can be made larger by rotating the coil faster, by using a stronger magnet, using more turns of wire, and wrapping the wire around a soft iron core. So again, this links us back to the principles that we looked at in electromagnets. Okay, especially the soft iron core and more turns around the wire. Okay. So there's 4 things to remember. The size and the induced potential difference can be made larger by rotating the coils faster, by using a stronger magnet, and using more turns of wire. Okay, so this diagram shows the potential difference waveform produced when the generator is rotated twice as quickly. So when it's rotated twice as quickly, obviously it's going to be faster. So the maximum, there will be 2 effects, okay? The maximum potential difference is twice as large, okay? So you can see it's going all the way to the top. So you can see same, so this is when it would be horizontal. Okay, so this is when it would be vertical, so like this. You see potential difference is 0. Horizontal potential difference is at its greatest. Then again, when it's vertical again, potential difference is, induced potential difference will be 0. Then again, it's horizontal, and the induced potential difference will be same as here, point. So if you say A, B, C, D, so we put same as B, but it's just in the opposite direction, okay? So if the generator is being rotated twice as quickly, you're producing as twice as much potential difference, and also the frequency is doubled. So who can tell me what the frequency is when we're looking at waves like this? What do we mean by the frequency? What do we mean by the frequency? What do we think? What is the frequency? What's frequency when it comes to waves? Not exactly the pitch, no. Sorry, yes, but then what would be the definition of frequency? What do you think? So frequency, okay. Anyone else have it? Yeah, so people are getting the right idea. So it is how often something is happening. Yes, good. So it's when you talk about it in waves, we're talking about the number of waves per second. Okay, so we're talking about the number of waves per second. So what this is basically saying is when the generator is rotated twice as quickly, you will have a maximum potential will be twice as quick. So the amount of induced potential difference would be times by 2. Also, the waves itself will be doubled because you can see if the frequency will be doubled. Okay, so there will be more waves per second. Okay, so that's what they mean by i.e. the interval between the peak is halved. Okay, so this peak and this peak would be, so we would have, this would be one wave. Okay, so this is one wave. So if we had something at twice as thing, this, let me draw it again. Rub this out and I can show it again. Okay, so, right, so, yeah, so the interval between each peak will be halved. Okay, so we can say there's actually, so I'm going to try and draw it out, but it might be. So there's actually, this is very badly drawn waves, but there's actually more waves per second. Okay, so the frequency is increased. So when you rotate the generators twice as quickly, you have the maximum potential be twice as quick and the frequency is also doubled. And the interval, so the interval between the two peaks is halved, okay? Okay. Right. This, okay. We're gonna look at this one slide before we go on our next break, okay? So the dynamo, okay, so this diagram shows the design of a direct current generator. So far we've been talking about alternating current, so AC. Now we're gonna look at DC, okay? That's called dynamo, okay? So the design of dynamo is similar to that of an alternator. However, the main difference that you'll see with dynamo is that it has a split ring commutator rather than two separate rings, okay? Two separate split rings. Now, it doesn't matter which side, so A, B, or C, D moves upwards, the induced current will always flow in the same direction. Okay, so that's the difference between direct current and AC current. With your direct current, you will always, you have a split run commutator, so the induced current is always flowing in the same direction. Okay, with AC, it will be changing directions. Okay, so remember if we go back to so we said here, sorry, yeah, so it's split ring commutator, whereas rather than it having two splits, separate slip rings. Okay, right. So we're going to go on our last final break. So if you guys come back around, so if you guys come back around 16 past, okay, We will be looking at the last things we'll be looking at are how microphones work, and we'll be looking at transformers. And then we will end the lesson by doing some exam questions, and then we'll do a Kahoot. We'll see how much time we have to do exam questions. We'll end with a Kahoot. Okay, so I'll see you guys in 15 minutes. I think someone put in the chat that I was on mute or that they couldn't hear me. Sorry, we were on our break. So we were just gonna make a start again. Can you hear me now? I don't know if you're able to hear me now, but earlier I wasn't speaking because we were on our break. Yes, okay, good, right. Okay, so then let's carry on. We're on our last little session. Okay, so talked about that. Okay, so the diagram here shows how a moving coil microphone works. Okay, so when sound waves reach the diaphragm, so remember sound waves are just vibrations. Okay, so when these sound waves, these vibrations reach the diaphragm. Okay, so this is your diaphragm. The diaphragm is attached to a small moving coil. Okay, so it's attached to the small moving coil, which then vibrates inside a strong magnetic field. So in this way, a potential difference is induced across the ends of the coil. Okay, so the sound waves are reaching a flexible diaphragm that is attached to a small moving coil, which then vibrates, and that's inside a strong magnetic field. Okay, so that is creating a potential difference. Potential difference is induced across the ends of the coil. When we use a microphone with a sound system, the induced potential difference is amplified and a current can then drive a loudspeaker, which enables an audience to hear the sound. Okay, so when we're using that microphone, the microphone with that sound system, the induced potential difference is being amplified so you can hear it louder. And a current can then drive that loudspeaker, which enables an audience to hear the sound. Okay, so that's how a microphone is working. Okay, so changing currents and fields. So the diagram shows two coils placed close to each other. So you have coil 1 and you have coil 2. So coil 1 is connected to a battery. Okay, so this one is connected to a battery. And coil 2 is connected to an ammeter. So it's connected to a sensitive ammeter. Okay, so coil 1 connected to a battery, coil 2 sensitive ammeter. So when the current is switched on, the ammeter in the second current moves to the right. Okay, so when the current is switched on, the ammeter in the second circuit moves to the right. Okay, when the current in coil 1 flows steadily, the ammeter reads 0. When the current is turned off in coil 1, the ammeter moves to the left. Okay, so then let's think about why does this happen then? So if we go to think back to the principle of when we move the magnet into the solenoid, then leaving that magnet stationary in the solenoid and then moving the magnet back out of the solenoid again, it's the same principle. Okay, a potential difference is induced one way when the magnet moves in, then the other way when the magnet moves out. So you can increase the size of the induced current further by putting an iron rod between the coils. So now the current in the first coil will produce a larger changing magnetic field, which induces a larger current in the second coil. Okay, so you can the reason why when the current in coil 1 flows steadily, when the current in the coil 1 is flowing steadily, the ammeter reads 0, and when the current is turned off in coil 1, the ammeter moves to the left, so it goes right, flows steadily, ammeter is reading 0, then when it moves back out, ammeter moves to the left. It's the same principle as us moving the magnet into the solenoid and then leaving the magnet stationary and then moving the magnet back out. Okay, so then let's look at how transformers are made then. So a transformer is made by putting two coils of wire onto an iron core. Okay, so you have an iron core and you have two coils of wire. Transformers also only work using AC supplies, so alternating current supplies. So that's a really important thing to remember. Okay, so they only work using an AC supply. So let's highlight that. So transformers only work using an AC supply. When an alternating current is supplied to the primary coil, a changing magnetic field is produced. So when you have current passing into the primary, So when you have current passing into the primary coil, you induce just changing magnetic field is produced. The iron core becomes magnetized and carries the changing magnetic field to the secondary coil. Okay, so the changing magnetic field passes through the secondary coil where an alternating potential difference is induced. So when a direct current is supplied to the primary coil, the magnetic field is constant, and then no potential difference is induced in the secondary coil. Okay, which is why we only works using an AC supply. So we have we have two different types of transformers. Okay, so we have two types of transformers. So we have step up and step down transformers. Okay, so transformers are useful because they allow us to change the potential difference of an AC supply. Okay, because we can change that potential difference. So you can supply, it can carry high energy, and then you can supply low amounts of potential difference to our homes. Okay, so the input PD, input potential difference, is increased from 2 volts to 12 volts. So when there are more turns, so when there are, I'm just going to highlight it. So when there are more turns on the secondary coil than the primary, the potential difference is increased. This is a step up transformer. Okay, so step up transformers, you have more turns on the secondary coil than the primary coil. When there are fewer turns on the secondary coil than the primary coil, the potential difference is decreased, and this is an example of step down transformer. Okay, so when it goes from 2 volts to 12 volts, there is more coils on the secondary, more turns on the secondary coil, so it's a really bad way of showing more coils, then that is step up because you're stepping up the energy, so the current. And if it went from more on the, so if we had 12 volts on this one, 2 volts on this, so this is our primary secondary coil, this will be a step down transformer. Okay, so that'll be our step down transformer, and it will have more coils on the primary. And transformers are really useful because they allow us to change the potential difference of an AC current. Okay. Okay then, so we can calculate the potential difference using this equation. Okay, so let's get back. Okay, so we can calculate the potential difference using this equation. So VP is the potential difference across the primary coil over Vs is the potential difference across the secondary coil, and that directly correlates to Np, which is the number of turns in primary coil, and Ns, which is the number of turns in secondary coil. Okay, so we can, if they asked us to work out the potential difference in a primary coil, we could work that out. Okay, so if they gave us the potential difference in secondary, and they gave us the number of turns in primary and secondary, we would be able to work out potential difference across in the primary coil. Or similarly, if they gave us all the potential difference and they asked us to work out one of the number of turns, we could also do that. So let's look at an example of this. And if the potential difference is increasing from primary to secondary, so primary, the potential difference goes up from primary coil to secondary coil, that would be an example of what kind of transformer. What kind of, what an example, well, if it has more coils on the secondary, therefore it has more high potential difference in the secondary coil, what kind of transformer would that be? What do we think? Step up, excellent, well done. And then if there's more on the primary compared to the secondary, then it's step down. Okay, so let's look at this question then. So an AC power supply has a potential difference of 230 volts. This is applied to the transformer with 5,000 turns in its primary coil and 250 turns in its secondary coil. Calculate the potential difference across the secondary coil, and then tell me, is this a step up or a step down transformer? Okay, so I'm going to give you guys 2 minutes to try and work. So first, try and work this question out. Let's write this out. Okay, so work out this question. First, work out the potential difference of this across the secondary coil, and then work out the whether it's a step up or step down. To help you guys, I'm going to put up this equation. So just work that out. So I'm going to write this equation on the next slide. So we're going to go, it's VP over VS equals NP over NS. So that's the equation. How would we work out the potential difference across the secondary coil? Give you guys 2 minutes to do that question. Okay. Okay, so someone's put an answer for the potential difference across the secondary coil. So would that be any more suggestions? Okay, give you guys another minute. We're going to do 15 more seconds, and then I'll go through it. Do we have any more suggestions for the answers? Any more suggestions? Okay, let's go through it then. Right, so first we know the equation is VP equals VP over VS equals NP over NS, okay? So we then put in the numbers that we do know. Okay, so the numbers that we do know are VP, we know that it is 230 volts over VS we don't know, and we know that In the primary coil, there are 5,000 turns, and in the secondary coil, there are 250 turns. Okay, so first what we can do is we can go 5,000 over 250, and the answer, put that just into the calculator, we will get 20. Okay, so we do 230 over Vs equals 20. So now we need to get this, we need to basically isolate this term, don't we? We just need to get what Vs would be. So Vs equals 230 over 20, which is 11.5 volts. So Vs equals 11.5. So we know the potential difference is 11.5 volts. Okay, so is this a step up or a step down transformer then? Well, if the primary coil has 230 volts and the secondary coil has 11.5 volts, is this step up or is this step down? What do we think? What do we think? It's going to be step down, isn't it? Because it's going from 230 volts to 11.5 volts. It's going to be a step down transformer. Okay, so we use transformers to transfer electrical power from the primary coil to the secondary coil. So most transformers do this very efficiently, and there is little loss of power in the transformer itself. Okay, so for a transformer that is 100% efficient, we can write that power supplied to the primary coil equals the power provided by the secondary coil, because there's no power being lost. So the equation would be Vp times Ip equals Vs times Is. So Vp is the potential difference across the primary coil. Ipi is current, so current in the primary coil, equals the potential difference across the secondary coil times the potential times the current in the secondary coil. Okay, so this diagram shows electricity generated in a power station is distributed across the country, across national grid. Okay, so you'll have 25,000 volts. It'll go through a step up transformer, and we'll have 250,000 volts, and then you'll have a step down transformer, so you can have it at safe voltage of 230 volts. Okay, so power is transmitted around the country at a potential difference across as high as 400,000 volts. So what's the reason for it? So there's a very good reason for it. Can you think of the reason? So the reason why it's transmitted across at high voltages, it's by stepping up that potential difference to a very high level. Power is transmitted using much lower current. So when high current flows through a wire, energy is used to heat that wire up. By keeping that current low, less energy is wasted and the whole system is more efficient. So when you have potential difference that's very high, it means that the power can be transmitted using much lower currents. And if you had high currents flowing through the wire, then we will use that energy to heat up that wire. So we will actually have a loss of current through heat. So by keeping that current low, less energy is wasted, and the whole system is just much more efficient. So that's why we transport energy at very high potential at very high voltages. Okay. So this diagram suggests two ways of transmitting 25 megawatts of power from Yorkshire Power Station to the Midlands. 25,000 volts from power station could be used to send 1,000 amperes of current down the power cables. And the potential difference could be stepped up to 250,000 volts, and 100 amperes could be sent along the cables. Okay, so you have A, which is 25,000 volts, and you're sending 1,000 amperes. And 250,000 volts, you're sending 100 amperes. Okay. So by how much power would be wasted in heating the cables in each case, given that 200 kilometers of cable has a resistance of 10. Okay, so how could we figure that out? So power lost, the equation for it is power lost equals potential difference along cable times by current. Okay, so we do that for each situation. So we go here, so we do that for, so the current here, the big go A and B. So by stepping up the potential, the potential difference to a very high level, power is transmitted using much lower currents. When high current flows through the wire, the energy is used to heat up the wire. By keeping the current low, less energy is wasted and the whole system is much more efficient. Okay, so that's basically what this is showing. Okay, so on to the last bit. So we're going to look at this before we move on to exam questions. So can we try and fill in this table? Okay, so I'm going to number them 1, 2, 3, 4. Okay, so I want you to work out what each one is. So what number 1 would be, number 2 would be, number 3 would be, number 4 would be. And then we're going to see if it's a step up or a step down transformer. So let's first do number 1. Remember the equation, Vp over Vs equals Np over Ns. So what would number 1 be? So have a go at trying to figure out what number 1 would be. What would number 1 be? We'll just do a couple of them, so just so that I know that you guys have understood the idea behind it. Number 1 would be, so use the equation. I want everyone to have a go. Has everyone had a go? What do we think? Should we go through it? Okay, so let's go through it then. So they want us to work out primary terms. Okay, so we're doing number 1. They want us to work out primary terms. So let's substitute in what we already know. So we know secondary turn, the number of turns in the secondary coil is 50. We don't know what NP is. That's what they want us to work out. We know that the secondary primary potential difference in primary volts is 240 volts. And secondary, sorry. Okay, so then we know that potential difference in secondary coil is 12. So we have to try and work out what NP is. So we would do 240 divided by 12, which would give us 20 equals NP over 50. And then we have to, how would we get what 20 is? So how would we get what NP is? Any ideas? Yeah, excellent, well done. So it's just 20 times by 50, which is 100. Okay, so the number of turns in the primary would be 100. Number of turns in secondary will be 50. Okay, so is that a step up or a step down transformer? Oh, sorry, yes. Yes, so it would be 20 times by 50 is 1,000, not 100, sorry. Yes, so it'll be 1,000 turns. So would that be a primary or would that be a step up or a step down transformer? Would that be a step up or a step down transformer? Step down, because there's less coils in the secondary one, isn't there? Okay, let's then do this one then. What would 2 be? What would be the answer to this one? What would be the number of primary turns in this scenario? So use the same equation, have a go, see what you get. Okay, I'll give you guys a minute to try and figure that out. What do you think? Okay, so I'm going to put it down. Okay, any more suggestions? Any more suggestions? Any more? Okay, let's go through this one then. So we just substitute in what we already know. Okay, so we know that VP is the potential difference across the primary coil. So that is 33,000 over the potential difference across the secondary, which is 11,000, equals primary turns we don't know. So that's what we're trying to work out. So NP is what we're trying to work out. And the number of turns across the secondary coil is 5,000. Okay, so we can just simply do 33,000 divided by 11,000, which gives us 3. Okay, so we say that 3 equals NP over 5,000. Then how would we get what NP is? So we'll just do 3 times 5,000, which is 15,000. Okay, so the number of turns on primary will be 15,000. So is that a step up or is that a step down transformer? Is it step up or is it step down? Step down. Excellent. Well done. Yes. So I'm hoping you guys are getting the hang of this now. Okay, so that will also be a step down. Okay, so we're going to move on. We'll come back to this if we have time at the end. And we're just going to quickly look at some exam questions, okay? So we're going to look at some exam questions and then end with the Kahoot, okay? So complete the description of the device shown below by drawing a ring around the correct line in each box. So the device is the device being used as a what? The device is being used as a, is it an electric motor, a generator, or a transformer? Okay, so we have some of the answers in. Any more suggestions? Any more suggestions? Okay. Oops. So it's being used as an electric motor, and you can see because it has an axle and it's being turned around. So it is an electric motor. Okay, next question. The coil needs a flick to get started. Then one side of the coil is pushed by the cell, the coil, or the force, and the other is pulled, so the coil spins. So how is the one side of the coil being pushed? So bearing in mind it's an electric motor, how is the one side of the coil being pushed? Is it being pushed by the cell? It's being pushed by the coil? Or is it being pushed by force? What do we think? What are we thinking? Any ideas? So the coil is being pushed by a force, okay? Next question. It's just 2 changes to the device, each of which would make the coil spin faster. So what could you manipulate? What could you change in this design that would change the, so that the coil spins faster? What could you change? What are the 2 changes that you could do to the device to make it spin faster? Any ideas? What do you think? Okay, let's have a look at the answers. So yeah, like I said, it's the force that's the one side of the coil is being pushed by the force and the other one's pulled, so the coil is spinning. And two changes to the device that would make it spin faster. You just think more powerful magnet, okay? So you can reduce the gap between the magnet and the coil, increase the area of the coil, more powerful cell, you could do more turns, okay? So think back to the things that we talked about. 4 factors that could increase it. So more powerful magnet, we could do more turns of the coil, reverse the polarity of the cell. So like you can turn the cell the other way around, and reverse the polarity of the magnet. So turn the magnet the other way up as well. Okay, so I think we should do a Kahoot. So I'm just gonna share. I'm going to put up a Kahoot pin. Hopefully you guys can join once it loads. Okay, the pin is just joined. Okay, so that's the pin. So I'll put the pin up in the chat. You guys could all join. So 3, 6, 10, 4, okay. You could join the one more person could join. Put the pin into the chat. We're only gonna have 2 players today. Okay, I think I'm gonna make a start. I don't know if the other person is joining. Let's start playing then. Okay, good. Next question. Next. So it's A. Okay, next. Okay, next question. So it's asking where is the North Pole? So that would be Y, because remember the magnetic field lines always go from the north to the south, and you can see these arrows are pointing in this direction. Okay. Yep, next question. Well done for getting that right. Okay, next. So what do the black lines show around the magnet? Good. Next. Next. Which of these materials is not magnetic? Yeah, brass isn't magnetic. We talked about that earlier in the lesson. Next. Which of these is not a way of increasing the strength of the electromagnet? Yeah, more resistance is not. Good. Next question. Okay. So transformer has got 6 questions right in a row. It's very impressive. Well done. Which of these can be used in a permanent magnet? It's steel. Okay. Next question. Okay. Next question. Yes, so remember the iron core. Okay, next question. So remember, magnet and a magnetic material will always attract. Okay, next. What's the name for a coil of wire that's with a current running through it? So that's a solenoid. So you have solenoid is when it has a long coil of wire and you put a current through it and that becomes magnetic. Okay. Next. We have 2 players. The magnet and first place. Well done. Okay. Right, so, okay. So that's going to be the end of our lesson today. Can you see me? So well done for coming, well done for staying. I hope you actually been able to gain something out of it. And yes, thank you. And I'll see you later. Bye. Bye.